Hello everyone, this is the fourth video of module 2 statistical models in simulation. So in this video I am going to discuss on the remaining two distributions related to the continuous distributions. So that is log normal distribution and triangular distribution, and also I am going to discuss on the topics of Poisson process and empirical distribution. So first I am going to start with the log normal distributions. So log normal distributions here, a random variable x has a log normal distribution if its PDF has a form, that is PDF is given by f of x will be equals to 1 by square root of 2 pi sigma x exponential ln x minus mu divided by 2 sigma square whole square if x is greater than 0, or else if f of x will be equals to 0 if x is not greater than 0. So for this log normal distribution, the mean and variance is given by the following formulas here. Mean will be given by e of x will be equals to e to the power of mu plus sigma square divided by 2, and the variance v of x will be equals to e 2 mu plus sigma square by 2 of e to the power of sigma square minus 1. So this is about the log normal distributions. Next is triangular distribution. A random variable x has a triangular distribution if its PDF is given by f of x will be equals to 2 of x minus a divided by b minus a into c minus a if x lies in between the range a and b, and if x lies in between b and c, then we will consider 2 of c minus x, c minus b into c minus a, or else we consider it f of x as 0, where a is less than or equals to b, less than or equals to c. The mode occurs at x is equals to b. So mean e of x is given by a plus b plus c by 3, and mode will be given by b, which will be equals to 3e of x minus a plus c. So this is about the triangular distribution and log normal distribution, which are related to the continuous distributions. So once we are clear with the continuous distributions and the discrete distributions, then we move to what actually is a Poisson process. So here the Poisson process definition we are going to see first. N of t is a counting function that represents the number of events that occur in within the range 0 to t. So how many events occur within the given range? That is, here we are considering from 0th clock time till t clock time, a counting process n of t. That is, n of t is nothing but the number of events. N of t means number of events that takes place within 0 to t. If t is greater than or equals to 0, is a Poisson process with mean rate lambda if arrivals occurs one at a time, and n of t, if t is greater than or equals to 0, has stationary increments. Number of arrivals in t, t plus s depends only on s, not on starting point t. Arrivals are completely random, and the n of t, t greater than or equals to 0 has independent increments. Number of arrivals during non-overlapping time intervals are independent. Future arrivals occur completely randomly. So here also we go through the two different the properties of the random numbers. If those both properties are satisfied, then only this Poisson process will can be accepted for the random arrival of the events. So here first moving to the properties of the Poisson process. So there are two properties related to the Poisson process. They are random splitting and pooled process. Depending on the arrival of the events, we can randomly split them, or we can pool the different events which are occurring. So there are two types. First one we'll see with the example. Suppose that jobs arrive at a shop in accordance with the Poisson process having rate lambda. At lambda rate, some jobs will be arriving, or some customers will be arriving. Suppose further that each arrival is marked high priority with probability 1 by 3. If the probability value is considered as 1 by 3, then the high priority arrivals are marked, and low priority with the probability 2 by 3. Then type 1 event would correspond to the high priority arrivals, and the type 2 event would correspond to the low priority arrivals. If n1 of t and n2 are of t are just defined, both variables follow the Poisson process with rates lambda by 3 and 2 lambda by 3 respectively. So n1 of t is nothing but the number of arrivals which arrive at the probability of 1 by 3, and n2 of t considers, or it consists of, the number of arrivals which arrive with a probability, a low probability or low priority, with a probability value of 2 by 3. And If n1 of t and n2 of t are just defined, both variables follow the Poisson process with rates lambda by 3 and 2 lambda by 3 respectively. So this is about the random splitting. We are going to split the events based on the probability of occurrence of each and every event. We are going to distinguish them into high priority and low priority events, and high priority is given by the probability 1 by 3 for example, and if it is of low priority then the probability is given as 2 by 3, and addition of these two will give the actual number of arrivals. Second one, a Poisson arrival stream with the lambda 1 equals to 10 arrivals per hour is combined. That is, it is pooled with a Poisson process arrival stream with lambda 2 equals to 17 arrivals per hour. That is, we are combining both these arrivals, lambda 1 and lambda 2, and the combined process is a Poisson process with lambda equals to 27 arrivals per hour. So it is a sum of two different types of arrivals. So this is about the properties, random splitting and pooled process. Next, moving to the Poisson process continued with this non-stationary Poisson process is characterized by lambda t, the arrival rate at the time t. The NSPP is useful for situations in which the arrival rates varies during the period of interest, including meal time for restaurants, phone calls during the business hours, and orders for pizza delivery around 6 p.m. The key to work out with NSPP is the expected number of arrivals by time t, denoted by v of t will be integration of 0 to t lambda of s ds. Relating stationary Poisson process n of t with the rate lambda equals to 1 and NSPP nt with the rate lambda of t. Let arrival times of the stationary process with the rate lambda will be equals to 1, be t1, t2 and so on, and the arrival times of the NSPP with the rate lambda of t be t1, t2, t2, then t I will be equals to reverse v of ti, tj will be equals to the power of minus 1 of ti. So this is about the Poisson process. Next, last thing which I'm going to discuss here is about the empirical distribution. A distribution whose parameters are the observed values in a sample of data may be used when it is impossible or unnecessary to establish that a random variable has any particular parametric distributions. So advantage of using this is no assumptions beyond the observed values in the sample, and disadvantage is that sample might not cover the entire range of possible values. So empirical distribution example, customer arrives in groups from 1 to 8%. Observations of the last 300 groups has been reported. Summary of this is given below. So here we can see group size, frequency of arrival, relative frequency and cumulative relative frequency. We have seen how to find out this, and here is a graph for the relative frequency and empirical CDF of the group sizes. So this is about the empirical distribution, and with this our fourth video, I'm going to end with the fourth video of this module 2. Thank you.